heart rate variability feature extraction. I'm just going to try to do that briefly before moving to the final thing, which is the translation side. So once you have the features, once you know those features and pointing out to a specific psychological state, so what do you do with it? And that's what we're going to try to do today. So feature extraction, we saw a little bit of IVUs and a little bit of EDA. So my recommendation is, we are not going to be able to cover a lot of things in 2 hours of feature extraction. So access the links, record your own signals and the ones that you want to try, and then start running things and start getting plots and start playing with it, because there's already a lot of time being saved having the scripts that you just, and they have their routines that I think they did a nice job creating all the libraries for you to be able to work with, but yeah, it's a matter of playing with the signals. So for heart rate variability, we mentioned that we have 2 different sensors, the ECG and the PPG. You can actually try to get heart rate variability using the camera-based sensor. So you try to get the heart rate, which is an approximation of the PPG. Those things are always not very accurate. So theoretically, what you have is basically the waveform of the ECG, then you have the R peaks, and then you extract the time series of the R peaks. What happens in reality is you don't have them as straight as you would like. Plus, you have a lot of noise that is related to the movement or is related to the position of the electrodes. Plus, these electrodes, although they're it's a pretty straightforward way to collect ECG, this is just based on 2 electrodes array. That means that it's not covering a lot of the electrical information that we are collecting from the heart. So when you go to the clinic or to the hospital, they will do 12 electrodes recording, which will give you a better shape and a better morphological features in the ECG. But this one is pretty much for exercise. So what you have is this type of signals. For instance, over here we saw baseline monitoring. We saw it yesterday. So the base of the ECG is basically moving. Over here you have a lot of movement artifacts related also to the muscles. Some people that have a lot of hair over here, they also have that. Or the breast, when you don't place the ECG, you place it a little bit down, you will get this thing. When the electrodes are well, in this one it doesn't happen, but sometimes when you connect the electrodes, instead of connecting it like this, you connect it like this, or you just switch a little bit of the size of the ECG, you will get the peaks inverted. So that's, those are some of the normal things that you will find when it comes to ECG. If you see them in real time, so what is going to happen with the spectrum when you're collecting the signals and when you're trying to do things in real time, which is what we want to do. We want to collect the signal, extract the peaks, and then compute some of these features. So you will see that depending on the motion artifacts that we have, see the variation of for instance, the power spectral density. So it's shifting. That shifting is not related to a person sympathetic activation or to a specific physiological reaction. It's just due to the algorithm that you are using to capture the peaks in real time. It's just missing points. It's just you are not using an efficient algorithm. You are not using a good peak detector script, and then the features that you are capturing in real time, you're just moving a lot. So this is kind of important to be visualized, because I would like to reinforce on the importance of doing a pre-processing and a good feature extraction, especially when it comes to real-time processing. Because if you want your robot or your system to change a behavior based on the variation of a feature that you are extracting, so you can be sure that the variation is not necessarily is not necessarily affecting the robot because the inner state of the person, but it's probably just because you own algorithm. So this not only happens with ECG, like if you go to EDA and the others, detecting features in real time is always quite challenging. Okay.
Another question is for the polar sensor, they're designed the sensor to be used in exercise, right? Do they have some sort of like onboard processing for like countering all motion artifact? Because this is supposed to be used during exercise.
Yes, they have, and that's one of the, I would say, cool features of the Polar. So, whereas with the Shimmer device, the Shimmer also has some ECG, so you can also connect electrodes and get the ECG. But with the Shimmer device, if you use it, you will need to do the peak detection, strike the RR peaks, and then get them in real time to strike the heart rate. The Polar does that for you and gives you all the array, and they have embedded, I will say, pretty accurate algorithms to collect the RR and the heart rate in real time while you are exercising. So the sensor is supposed to be optimized for exercise plus movement itself. So yeah, so the sensor gives you that. They unfortunately don't have a lot of documentation on what are the algorithms that they implemented, but they have some information there, so you can add those to the article, because that's what we do as scientists. We don't say, oh, that's a black box, and yeah, let's do magic, and we're obtaining the heart rate. We need to go to the details. There's plenty of good studies comparing the Polar with the clinically valid ECG sensors. So you can also refer to those, like the level of accuracy of the sensor.
I have a quick question.
Yeah.
What is the difference between ECG and PPG?
Yeah, like from a physiological phenomenon point of view, one is collecting electrical activity, the other one is collecting just light incidence. So, there are like two types of instruments. They are both pointing out, or kind of like collecting similar information, is the activity of the heart. So one is collecting like how it is bumping and all the ECG, and the other one is basically the kind of like the blood pressure, the blood oxygenation, which is PPG. So this one has this specific morphological wave. The other one, the PPG, will be more like this.
So it's not possible to take out RR interval from PPG data because they both are different.
They have their own morphological notations.
Okay.
So instead of calling them R peaks, these are like, I think these are P peaks, something like that.
Okay.
So and there's an equivalent between the R peaks and the others, because at the end they're pointing out to the same, like how the heart is bumping. So, but heart rate variability analysis using PPG is more like a secondary thing. So it's more accurate if you do it with ECG. You can also do it with PPG, and I think depending on the type of application, it wouldn't matter a lot, the accuracy. I think we tend to focus a lot on, okay, how accurate is the sensor? I need the best sensor possible, but sometimes you don't really need the best sensor possible, because the fluctuations between one and the other, they are not going to affect your adaptive rules, which is at the end what you want. Like, if the heart rate bumps from, 100 to 120, then make a change in the behavior. And, with the PPG, it's like, okay, the error can be like 3 BPMs or 2 BPMs. So.
Yeah. So you're charging basically two different parameters from the cards. Maybe the ECG is more like the functionality, the electrical part, and the other is more the mechanical part, or the strength, how effective it's performing the heart or the.
Yeah, again, they're kind of like two different techniques for getting the same type of information. So ECG is way more clinical, it's way more accurate. But the O one is less intrusive. So you can use it over here, you can use it over here, you can use it, like I've seen people using it in many parts of the body, but you can collect the oxygen saturation. So, but at the end, if you see the heart rate collected from ECG versus the heart rate collected from PPG, they're pretty similar, like, depending on the context and everything, but they're pretty similar. So, if you plan to use PPG for heart rate variability, it's possible. We also have some scripts for that using the kit that I'm going to show you. And you know, for these type of applications that we are aiming here, we don't need to, you know, care that much about how accurate PPG is versus ECG.
I tried polar sensors last year and wrist variety sensors, and both of them the heart rate was similar.
What was similar?
Heart rate was similar. So
I mean, you start doing a lot of exercise with the wristband, probably the chest strap will give you way, you know, more accurate.
yeah, I was just sitting. So
Yeah, for seated is pretty good. So there's another interesting thing when it comes to getting the interval. So imagine you have the ECG, you have the peaks, then you strike your intervals. But then, you know, since you're moving a lot, since there's a lot of algorithms for collecting the R peaks, so you will probably end up with a, you know, let's say 20-minute session of the ECG. You would end up with something like this. These are the RR peaks, the RR intervals. I don't know if you noticed this, like, you know, all of these peaks, all of those are outliers. You know, you saw, I don't know if you saw in the other video that sometimes the script or the technique for peak detection was skipping some of the peaks. So you saw in the video, sometimes it's skipping that. At that moment that the algorithm is skipping that, it's giving you an outlier, because instead of like counting from this to this, so it's skipping one, so it's counting from this to this. So that's double. That can be 100, you know, milliseconds once compared to 700. So then when you make the plot of the RR intervals, so you will see that, you know, you got, well, 700, 800, 100, boom, and you have a big one. So these things are, you know, the outliers for RR intervals. So you need to do that type of correction. Again, I've checked the signals from the polar. When you check only the RR intervals, which it gives you, it still has some of these outliers, but it cleans a lot of them. I'm just showing here that you need to clear those. Normally you do that with a rule based on the standard deviation. So you check all the neighbors, and then you see, okay, if this one is 2 or 3 standard deviations from the previous one, then that's probably an outlier, and then you remove it. So at the end you will get something like this. If you don't do that, so if you don't remove the outlier artifacts, you probably will get significant results on something that is not real. So similar to, you know, what this paper was showing is basically by having a certain amount of non-corrected R peaks, you run the feature extraction, you extract all the time domain and frequency domain parameters, and then you make a comparison. Just by not extracting these, you can get significant results versus not significant results from a probability point of view. So coming back again to the importance of, you know, cleaning your data. So the article is basically showing that impact of cleaning those things. So at the end, you know, this is one of the signals from the RR intervals taken with the polar chest strap. That was like for 4 to 5 minutes, person running, not running, but, you know, kind of like moving regularly. So you should see something more or less like this. So when you see, you know, a lot of lines and things like that, that's probably all lights. But when you see something, you know, smoother than that, then probably that's a good signal. And you can see the histogram as well. So the histogram is normally very Gaussian, especially when you get like more than 10 minutes of recording. Probably will see that there's always, you know, a Gaussian distribution of the heart rate. So that's a good way to just double check those things. So you get the RR intervals, you clean them all, and then you have, okay, this is my time series vector of the RR intervals. Now what do you do? So what you do then is there's two types of features, so two branches of features. The first is time domain. So you do know parameterize time, you stay in the time, and then you start extracting features. What are the most widely used features? And the one that you saw also in the table 4.1, they probably were talking to this. So when they mention on NN or RR, those things are related to the RR interval series. So standard deviation, root mean square. There's one that's called the triangular index, which is basically the area under the curve when you have the heart rate variability plot. And as a way to summarize heart rate variability is basically a good window to the autonomic nervous system. So parasympathetic and sympathetic. In time domain is a little bit more complicated to say, okay, this is more sympathetic than parasympathetic. But when you move to the frequency domain, that distinction is probably a little bit easier, or there's more research on it. So it's been investigated that people that are more resilient, so physically and emotionally more resilient, the heart rate oscillations are higher and more complex. So that means that in a person, let's say the less resilient person, we probably have like a distribution of the heart rate variability. If you just plot our intervals versus time, you will get there's a stressor here, and that person will have a specific reaction to that stressor. You got another one here, that person will probably react similarly. So it's going to be more stable, let's put it like that. So there's not a lot of reactions, a lot of accommodation of the sympathetic and parasympathetic nervous system towards the external stressors. Whereas when you have a more resilient person, you probably will have the same, but the behavior of that would be like it goes up, it moves, and it certainly is more dynamic based on the stressors that you have. That's why they say, more complex and higher amplitudes of the variability of your heart. That is a good a symptom of good cardiovascular resilience. Again, resilience understood as the way that our body, and especially our heart, is adapting to the different external stressors. So being more resilient is being able to adapt to those things. So you get a lot of overwhelming things, and you don't get saturated. So you don't get overwhelmed. So your brain, your heart can still pump oxygenated blood to your brain, which at the end will facilitate all the processing of all external stressors. So that's why all of these metrics somehow try to always get those little variations of the heart based on the external things that we have. So that's for the time domain. We have, again, all the scripts to extract all of those features that we were checking there.
Can you use HRV to normalize that variation in your sample size? So if you have people that are really resilient to change and others that aren't, can you use that parameter to create a baseline?
Which one?
The HRV, triangular index.
Oh, the triangular index?
So if I have a sample size where some people are really resilient, other people aren't, can you use that to normalize your other data you get?
Why do you want to do that?
So that if I'm checking how people respond to a certain situation, maybe I'm checking something, and just because I have a variance in the resiliency, I'm wondering if there's a way to
Make the less resilient sample to be more resilient.
making it less your data less dependent on the individual resilience of someone.
Mhm. Yeah, there's always attempts to use the different statistical techniques to basically get into, okay, what is normal, or what is good, or what is bad. The best approach that I've seen are actually, it's called a Practical Handbook of ECG. It's a 1,000 pages book for ECG, and they have tables with studies pointed out what are the what's supposed to be normal from all of these parameters. So you get that the normal plus the standard deviation, and plus and less the standard deviation. That depends on age, gender. Those tables are depending on age and gender, and then you kind of have a good idea on how people heart rate variability should be. So I actually did something similar for my PhD in order to, okay, how can we compare heart rate variability parameters from people to people? And I did kind of like a visualization based on what I'm just telling you. But time domain is, as I mentioned before, is not always a good approach to differentiate between sympathetic and parasympathetic, which at the end can help you to describe the resilience of somebody.
Sorry, I was just going to like a dot. Like actually we're going to the frequency domain.
Yeah.
I think it's easier to distinguish between parasympathetic and sympathetic. Right?
Yeah, we'll show you.
Sympathetic is less like
It's more like fight and flight responses.
low frequency, right?
I will show you here. But yeah, remember, sympathetic is more fight and flight. Parasympathetic is more rest and digest.
So the reason that you want to separate them and to want to measure them is because then you can associate the fight and flight as something stressful and the other one as something the person is getting relaxed. I mean, why we want to separate them?
Yeah.
I understand that.
Yeah.
I mean,
There's always this need in psychophysiology to say, okay, which part of the nervous system, especially the somatic nervous system, is giving me a contribution, sympathetic or parasympathetic. Most of the times, all the psychological states that we have been describing, depending on the context, you have it's like a game of the sympathetic activating, parasympathetic deactivating, or the other way around. So when it comes to more relaxation techniques, respiration techniques, kind of like rest and digest, you have an activation of the parasympathetic nervous system, but most of the time a deactivation. So what you want to see is what are the features from whatever physiological signal I'm measuring that are increasing or decreasing that activity, and if those features are related to one or the other. That's basically what, because the psychological states that you're having are described by the behavior of those physiological parameters. That's why you want to discriminate those. When we move from the time domain and then we go to the frequency domain, in a lot of physiological signals, you will actually see that that's when things start getting a little bit more interesting, because as we have seen in physiology, there's a lot of variations of people, and when it's difficult to capture when you see that chunk, the time series, 20 minutes, with all the signals that are happening. Frequency is pretty good in kind of like helping you to visualize the whole idea of the session, of the entire signals. So you apply this is the fast Fourier transform, for instance, and you get the spectrum of the signal. Then when you move to the spectrum, you do something like the polar spectral density to plot, who was the entire behavior of the RR intervals. And then you just plot there based on the ranges of frequency. What you will normally see in heart rate variability signal, so the RR intervals, this is plotting the RR intervals time series. So you will see mostly 3 bands or 3 ranges. The first is the high frequency power. So it goes to 0.5 to 0.4 hertz, and it's basically, this kind of like initial peak, like a segment of that peak that you will see is related to the high frequency. Low frequency is yellow, so that means more the left side of the curve. And then you also have like very low frequencies, like those are like really pushing a little bit hard to the left. So there's not a lot of research in a very low frequency, just because it's very specific to activities that are not normally associated, or with people that are not normally associated as healthy adults. Anyways, so interestingly, research has found that the low frequency are normally associated to the sympathetic. nervous system, whereas the high frequency is more associated to the parasympathetic nervous system. So at the end, when you get the entire session, and then you get your high frequency values, so you can somehow compare the metrics associated to one and say that that person was maybe more arousal, more excited, or that specific condition, stimulus activated more people from a physiological point of view. That's called autonomic activation. I'm a big fan of indexes or ranges. So that means what happens if we combine one signal and the other? What happens if we just get, for instance, the alpha and the theta and the beta of the left side and the right side of our brain when we are doing electroencephalography, for instance. So it seems that this radio is like a good way to describe what is called the balance between sympathetic and parasympathetic. Again, the balance is what we're trying to achieve as a potentially healthy behavior of people. So we don't want somebody that is always based on a specific stressor, always activating the sympathetic nervous system. So those are people are normally very impulsive. So when you see like somebody and you say something and then that person is always reacting. Dilara, what do you want? What do you want? That's like a person that is always activating the one. And in the other side, when you have somebody that's always a little bit like Melanie, like chill, like leaving alone. So you have that person that's always at least from a visual mirror, more like the parasympathetic. So what you want is more like a balance of both, depending on the stressors that you have. So that's why this is the type of behavior that we want. We don't want a person that is always reacting the same, sympathetically or parasympathetically the same way. You want somebody that's dynamically moving from one to the other.
I have a question. I think it's a bit counterintuitive that the sympathetic responses are like low frequency, because I thought like fight and flight should be really associated with high frequency responses. Can you just quickly?
But why would you when you move to frequency, it's hard sometimes to associate things in a good analogy. So that's why what would be more intuitive for you, low frequency being associated to parasympathetic?
Low frequency, I thought it was something slow, and then high frequency is something explosive and immediate, right? So I thought, like fight and flight, you're supposed to be, doing something really quickly, because usually you're like in danger, and then you involve the sympathetic responses, right? So I thought, should be high frequency.
Yeah. My understanding of this is, certainly we are recording the small variations of the heartbeats when they are being externally, pushed towards something. So what you're really recording is, like for instance, how was the change? How was this moment once compared to this moment? So when you have like those high variations happening, there is a specific kind of like principle on autonomic activation and deactivation that it doesn't work that much as I was mentioning here. It's not like a 0 to 1 gate. It's not like the sympathetic activation is up and then the parasympathetic is down. It's more like in between. So it's more like a game of one activating and the other deactivating. So when you kind of like go and get a little bit of a better sense of how those gates work, which, to be honest, I don't truly understand and don't fully understand yet. That's the way that the psychophysiologists have been using to better explain why one of the ranges better explains one or the other. This is actually very controversial. So, there's some psychophysiologists saying that, there's one component more associated to the other. But I like using this type of metric because I'm not a psychophysiologist, so I care more about the final application. You just tell me which metric is better, and then I will use it for the front end application. So yeah, fortunately, I don't have a good answer for that yet.
So you said this is only, is this only good for the, like checking an entire session, or can you check this frequencies only for individual events, like window sizes?
Yeah, when it comes to real-time application, yeah, it's also like a good way of recording little variances of people in 5 seconds, 10 seconds, 15 seconds. You normally don't use this in like small variations of 2, 3, 4 seconds. So when you try to do real-time applications, you try to do process signals in Windows and make decisions based on 20 seconds, 30 seconds of data, especially when you're using heart rate or EDA, which we have seen that is more like slow-paced data. When you're working with things like EEG or EMG, those are like a little bit faster responses, so you try to shorten the window of processing. So that's why real-time is a hypothetical construct, because you are not necessarily doing it in real time. You need that window to collect the data and make all the processing in order to infer the human state.
Right. Thank you.
So you don't have enough sample if your if your window size is big enough for the FFT algorithm? Is that why you can't do it?
No, it's a use case thing. It's case by case, or like defining the window and everything. So the best way to do that kind of like approximation is for you to try. So you get a user, you hook the person, you are computing the variables in real time, and then you see how do they vary, and then you start bringing the stimulus. And then you see if the changes that you were expecting in that specific metric are actually happening when you bring the stimulus. The stimulus can be, the robot doing an activity, or when you add the person to a stress. Normally psychologists use those tests that are like torturing tests, which like those tests, like they're really like, the flashing screens, or when they are like putting a lot of math tests to check the workload of people when they're doing something. So that's kind of like the way you push people towards what you think is a little bit of extreme frustration. So in games I tend to push the game difficulty to frustrate people. So in a Tetris game, that would be like the pieces falling down like this. So people get really stressed, and then you check the reaction of that people when they're stressed. So you define the limits, and then once you have those limits, then you start narrowing down the variations you want to define your adaptation.
Sorry, I just want to come back to the
question.
One way that for me is easier to understand this. So if you think about sympathetic, you have to remember that the heart rate is going to increase, right? So it's going to be bumping and bumping and bumping. So the heart rate variability is going to be super short. So for sure, it's not going to be a peak of frequency because you won't have time, right? Whereas in the other, the heart is going to slow down the heart rate. So it's going to be top. So you have a peak, a big peak, a big peak. That makes sense what I'm saying? So
And if you check the because I think what Kevin also we are not thinking the same when you look, I guess because of engineering. So big frequency means that a wave is moving quite fast. So if you think about the heartbeat, so if you go fast, then the heartbeat is also a higher frequency. But then if you check the RR interval, then they're compared to something else.
Yeah.
So it's
the amplitude is shorter, but what Alex is saying is the RR intervals are shorter as well. When the heart rate is bumping faster, like the heart rate is increasing, whereas the RR intervals are decreasing because the distance between the intervals are, slower. But you see, that's why it's also a little bit of a controversial, because you say, okay, sympathetic is always heart rate bumping more and more. And you remember the cemetery case they brought here, like you're super afraid of what can be happening, and then your heart rate is.
And also those changes are very small, right? Because if you think
check the numbers.
High frequency is nothing, like 0.1 and 0.4 hertz is nothing. So it's like very subtle changes.
Sorry, Trevor, you were about to say
Yeah, I was
something.
just gonna say in terms of actual intervals of time, like 0.1 hertz is over 10 seconds, right? So I kind of thought of it as maybe the sympathetic event happens over the duration of 10 seconds.
Yeah, that's why I'm saying it's important to always check the context of the entire activity that you are doing, because it can be an activity where there's plenty of more sympathetic activation happening. So you're gonna have more contribution from one side than the other.
Yeah, sorry. I thought that it was going to, you from the video of yesterday with the bear. I thought that these two need to be more extreme to kick them out, like to really measure them, because now we are talking about some easy things like math problems or I don't know Tetris, and you say that also you can measure changes in the sympathetic and parasympathetic. So you don't have to go to the extreme to bring a bear and you know. No. So, but that means that I suppose it's more difficult to differentiate between them because, as you say, they don't go 0-1, they compensate, so it's more difficult.
It certainly is, and that's why when you're trying to compare among conditions, like you really need to be careful about your experimental design, because if you're trying to see what are the differences between behaviors of robots that are not very much, the changes are not like well established, then probably you're not going to find anything in physiological metrics. I mean, that doesn't mean that those the reaction of people by those two conditions are not like in place. That only means that through the lenses of physiological sensors, probably they are neglected. So probably you are blinded if you use it. That's why physiological signals is not something you can use for every other experiment. It's not like, you really need to be careful with the design and what are you trying to study. We have this. We actually I don't really remember Jesse and what the name of the other girl? The one that were using Iris. So we had two undergrad research assistants taking a closer look. They were the ones developing the application for the polar that can record the data and stream the data. And they also were checking the Python libraries for doing that. If you are more comfortable with MATLAB, so I just posted yesterday, the toolbox that I did, and they're all the toolbox that you can use for that. But the interesting thing with this libraries is called NeuroKid. Is certainly is bringing a lot of the things that you will need to extract all these features, similar to what SAT and Isha were doing yesterday. We didn't talk that much about the non-linear. So you have time domain, frequency domain. There is another one that is called. Are you guys familiar with the concept of Poincare plots? I think Christopher, most of the mathematicians use this kind of like Poincare plots. It's basically plotting different series in different moments, one against the other. So you get RR intervals in time 1 versus RR intervals in time 2, and then like you keep plotting all those points, and then you see what is the distribution of them. So it seems that there's a lot of interest in using Poincare plots for heart rate variability data, and they can extend our understanding or the variation on sympathetic and parasympathetic nervous system. So there's also some interesting tools there for that. If you click this one, it's gonna bring you to the toolbox. It's called NeuroKid. There's more and more kits appearing for working with Python in this type of signals, but I think it's pretty straightforward the way that they work here with heart rate variability. They give you all the time domain and frequency domain metrics that we were talking. They have methods to extract those based on it's always based on the RR intervals. So after you get the RR intervals as clean as possible, so don't necessarily trust 100% on the raw RR intervals that this sensor is giving you. Just take a closer look and see if you can clean it a little bit to get rid of the outliers that I just showed you for the RP protection. So you will be able to extract most of the features over here. So they also have some examples for the PPG signals, and how can you extract also features from the PPG. I don't remember if this is the one, but in a sense they do have very good documentation on how to run a heart rate variability analysis using both the ECG and the PPG. So the toolbox is there. We haven't tried the PPG heart rate variability. I think at some point we had some troubles with some of the libraries when we were working with the students. But I mean, if you're planning to use that specific signal, this is definitely the toolbox that you need to first check before starting, developing your own things. So it's supposed to be a friendly. That was created for not for, but the main end users for this was supposed to be psychologists. So they say like you can analyze physiological signals with only 2 lines of code. So kind of like something similar to what Sarah Nisha did yesterday. So heart rate variability, NeuroKit is good. We have developed our own libraries for that. So of course, I didn't cover a lot of the ECG details. This is more heart rate variability, peak detection, time domain, frequency domain. The point credit plots are an interesting non-linear analysis of that, but that's more or less covers feature extraction in ECG and heart rate variability. So that was the content missing yesterday. Questions?
So how can the nonlinear one, can you give an example of what that might show, given that it's 2 different timelines? And how would you?
Yeah, to be honest, I haven't studied, I haven't myself used the nonlinear descriptors for heart rate variability. I have seen cases, but mostly for long-term, 24 hours of recordings. So those plots are supposed to be good to create like clusters. So when you can see like day. So what is the cluster of the heart rate variability when during the day, during the night for this type of person once compared to the other profiles.
So it's like person 1 and person 2.
Yeah.
Okay.
It's kind of like good to also make comparison across people, but it's more like a recent technique for that, similar to all the nonlinear descriptors for all the physiological signals. They're still just exploring those things, just because the way of accessing the hardware is being accelerated by the development of wearable devices. It's not like, we're just recently putting our hands on the signals. It's just we have plenty of more data and more access to the signals right now what we had 10 years ago.
It's difficult to distinguish like parasympathetic, sympathetic responses in the time domain, but it's easier to do that distinction in the frequency domain.
When you work with heart rate variability, yes.
When you work with heart rate variability, can you say I only care about the sympathetic responses, just delete all the high frequency responses in the frequency domain, and then do inverse Fourier transform, and then get back to the time domain?
Well, certainly the analysis that you do is a little bit of that. Like you identify what you want to see, like anxiety. Sometimes anxiety is more related to the sympathetic activation. Then you check what are the features that are related to the sympathetic, the high frequencies, and then you just get those features, which are basically the weight or the contribution of that range in the power spectral density function. Then you weight that, and then you have that little number onto that. So in a sense, what the analysis of frequency domain is doing when you do the statistical analysis is a little bit of removing one component or the other. Not removing, but you're just paying more attention to it.
So I guess as a summary, if you want to make the robot relax a person, you have to trigger the parasympathetic system. If you want to make, prepare a person to be, for an exam or something that needs a bit more to be more alive, right? You need to trigger the sympathetic kind.
Yeah, that's a very rough way of seeing it, but yes, that's what you want. At least initially, you want to be able to trigger that. Doesn't mean that you're going to be sympathetic all the time.
Yeah.
The moment that you're interacting with the robot, because that can even be dangerous, as we saw. Like you remember we saw an example of the bird. At some point, the guy was just freaking out. Like if you push very much towards that, a robot with a knife, there, that can be complicated. But yes, you want to measure this triggers on the sympathetic and parasympathetic. That's why it's important for you to choose the right signal and also to choose the right windows that you are checking those things, because some signals are slow paced and some others are like really fast paced. Heart rate variability is better in the time window, whereas EDA is better into, okay, the GSR, okay, that's kind of more well defined. So that's why combining those signals sometimes better. So yeah, that's a good summary. So yeah, more relaxation, like decompressing, is related to parasympathetic, and you try to record those, and the same thing or the opposite with the sympathetic. So 1 hour. The second part is indeed a little bit shorter, which is the pairing, which we would like to talk more about what happens once we detect this. And we will also show later today that we have been creating some tools to actually stream the data in real time, some scripts to be able to compute the features in real time, and we actually have a use case of closing the loop with physiological signals, but still the infrastructure that we are trying to build is it's not as usable as we all want. And it takes some time. I mean, it took me fairly one PhD back in Portugal to kind of like build an infrastructure for using this in the world of games, which is a little bit easier than robots, because every robot is kind of like programmed from a different software frameworks, whereas the games can be all summarizing an only game engine. So we've been trying to build some infrastructure, but it's a little bit tricky. So this second part of the talk is more about closing the loop. Like we talked the first day about sensing, how do we measure, how do we record a signal. The second is more the feature extraction, which goes to the analysis part. And then this part is more about the translation. This is the suggested reading. It's basically a paper of some guys at NASA that were summarizing a lot of the efforts that they were doing towards creating closed loop system using physiological signals. So the reading is mostly throwing you examples on how do you use this, what are the features that they were using, and what are the applications that they did. As I mentioned before, the concept is called biocybernetic loop. It's a little bit of a fancy word to describe a closed loop system that uses physiological signals as input, but that's what you're going to find in the literature. What do you want when it comes to a biocybernetic loop? You want users to be exposed to a system that is recording physiological signals in real time, is analyzing those signals in real time, is interpreting those signals, inferring a psychological state or a human state, and then reacting accordingly. How do you do that? You first do a sensing, so you can record signals from the users. So EEG, CG, DA, EMG, so a lot of the signals that we have seen. Then you do an analysis, you process, you select the features, and then you extract those features and compute them in real time. So you have them any 10 seconds, you are getting the high frequency of the heart rate variability. So you're getting a vector on that. And then you want to do a translation. But when it comes to doing the translation, is like, how do you ensure that the person is somehow feeling or like the system is somehow reacting accordingly to that? That is triggered by behaviors. When it comes to the example of a robot, would be a special behavior of the robot, would be a feedback of the robot, so lights, so screaming, so sounds, so whatever you can recreate in the robot. Or you can make adaptations of the specific behavior of the robot. So you just program your robot to behave in a certain manner, and based on this analysis, you just trigger those behaviors. And then, the feedback is coming back to the user, so that's why it's a closed loop system. That's kind of like in a nutshell what we want to do. The problem with this is, why do you want to use that? Why do you want to create physiologically adaptive systems? I've seen three categories, but you know, most of the time, a lot of the physiologically adaptive systems fit into it. So one is assistance. So you want to prevent people to getting into a bad psychological state. So let's say you want to prevent people to be super stressed. You want to prevent people to be very much anxious about a situation. So you trigger the behavior of the robot based on certain levels of stress. So you detect the stress and then you create a behavior in the robot or in your system that is supposed to relax the person, theoretically or pragmatically. So assisting people. So, but I've seen a lot of interesting application in rehabilitation, for instance, detecting muscular fatigue, and then reducing the level of challenge of the physical activity when they are doing rehabilitation. Or there's not a lot of, unfortunately, examples of robot-assisted therapy that is physiologically adaptive. But good examples of this are, you know, some of the things that we have been envisioning here in our lab, in which, you know, a robot can certainly behave differently and try to reduce some negative impact of diseases or neurocognitive states. So that's more for the assistant side. Then we go. This is more related to keep people more engaged, to keep people in the flow. So you don't want people to get bored. You don't want people to get really frustrated because the activity is very hard. So what you do is record the balance of the sympathetic and parasympathetic activation when people are interacting with an activity or a task. You want, I know you have seen in psychology, there's something that is called flow, where you basically want to keep, we saw the arousal model of flow. So you basically don't want to put people here or here, but you want to keep people in the good state of optimal arousal, because they are optimally engaged with the activity. And that has different behaviors depending on the signal that you have. So keeping people engaged, keeping people entertained. The last one is more like, you know, who can you use the explicit feedback of physiological sensing as a way to help people to train their physiological self-regulation. So if you remember when we talked about biofeedback, we were saying like clinicians were using this in the 70s and the 80s to basically allow people to show and be displayed by their own signals and allow them to reduce or increase their levels of physiological stress. So you can also use physiological adaptation to, you know, as a way to educate people in, you know, their own physiological regulation skills. I always like to brainstorm a little bit into, you know, you guys have seen sensing. We saw already analysis. We haven't seen a lot of the challenges when it comes to translation, but I like to just throw some ideas and brainstorm some of the ideas that you think that you might encounter, or you probably have encountered already, when it comes to creating these applications on each stage. So, for instance, you know, we have seen already the sensors and how do they work and how, you know, what are some of the challenges that we have there. What do you think can be like the main challenges in the initial stage in sensing?
Motion artifact.
So we mentioned already like movement and motion artifacts. What else?
So it's a contact. Contact, like maybe the contact is not proper, and then you get.
Oh yeah, we were also discussing when you put the electrodes, like, you know, you saw that sometimes they can move. You have a skin contact sometimes.
Accuracy, just to place the sensor in the specific anatomical part.
This is more like when placing the sensor.
Placing, electrode placing.
What else?
you're trying to do something with your hands, you don't wanna measure and you're using your hands.
So the sensors can be obtrusive, you say?
Yeah.
Yeah. Hey, have you seen this movie? What's the name of that? Negro de Naranja Mecânica?
Clockwork Orange.
Yeah, have you seen that one? There is a scene in that movie where like there's a guy and they open their eyes and they put a lot of sensors over it and they relax. And now relax. That's pretty much the obtrusiveness of the sensors. Like you want to study people when they natural responses, but then you're throwing a lot of sensors to them. So that's not always the case. I mean, now we're getting better and better into that, but that still happens. Even getting the chest strap sensor, like it takes some time for you to get used to. You have a sensor over there. What else? Yeah, we saw as well that, here at the lab we can control a lot of variables. When you go out, like the performance of the sensors in the field, that's a different thing.
Because battery life of the sensor as well.
Battery life. Yeah, when you're doing, it has happened to me, like I'm in the middle of the experiment and boom, the battery, something happened with the battery. Especially when you're doing like real-time experiments, like you're streaming a lot of data, you're asking, most of the time you need to go around the sensor hardware, so you cannot use the regular hardware, so you need to kind of like hack it a little bit, so you push it towards the limits of like, give me all this data in a 100 sampling frequency. So the sensors are not, like smartwatches. When you have a smartwatch, the heart rate measurement that you have is not like every second. This is like every 5 minutes. It's just turning on the sensor, getting the reading, turning off the sensor. When we did experiments with wearables and recording PPG, heart rate in real time, the battery of a one day battery of the watch, was running out in like 15 minutes, just because the sensor was always on and the wearable was not, supposed to be used like that. So that's the battery. Yeah.
And you can put hardware software issues, right? You have Bluetooth, you have everything.
Communications.
You said communication, yeah. I will try to show you an example of a physiologically adaptive system with the VR headset, and you will see that some of the problems that I have are nice actually. The communication, because the sensor is connecting for the computer via Bluetooth.
I was going to ask you yesterday, like maybe it is a problem as well. Do you have have you experienced any type of problem when it comes to detect different signals from the same device at different sample rates? Because you have the accelerometer that is, 100 hertz. Then you have maybe once embedded the EMG, this 2000. So how can you do that? It's just like.
Yeah, most of the, it's cool to have one single sensor that can record multiple physiological signals. And that's actually one of the goals of the people working in biomedical sensor development. However, that comes with a lot of pros and cons. One of the pros is like, one of the cons is, indeed, even though you are recording EDA and IMU plus PPG signals, all of them, they certainly need different sampling frequencies, so because they don't react to it. So in order to have the same timestamp, you need to record them mostly. You use the sampling frequency of the one that has the highest sampling frequency, because then you can use in the pre-processing stage, you can use up sampling or down sampling, which was a little bit what Isha was showing yesterday. You remember that she was getting the EDA, was like 2050 hertz, but EDA you don't need that. She was really downsampling that to 40 hertz, and this is still certainly a lot for that type of signal. So
You use one, okay.
you just use you use the highest, and then post processing you use the downsampling analysis. Any other?
Human factors. Or intrapersonal variability.
Yeah, intra and inter. Yeah, intra and inter. Yeah. think that's important always to consider those, because again, that's why it's tricky when you try to use databases of certain people in a certain context using a specific type of technology, and you try to create models for different people that are going to be using this, probably similar signals but in a different context. So because of this, like, it's not super popular to work with databases in physiological computing because everything depends pretty much on the context.
It's also a way, right? So these tables that you're saying is a way that you can save your experiment. So if you find a person that is an outlier and you don't know how to kick him out, so you say that this person has a, I don't know, heart variability that is outside of the normal range for that type of person, gender and BMI. Then you can say, okay, this person doesn't fit the normal tables of data, so I will remove him from the experiment, so it will maybe save the rest of the data.
Yeah, sometimes it's good to try to do a screening test before, and even during the resting, you will be able to see. I did that with all the adults, and I detected that there was one guy with bypass. So the behavior of that person was always the same. So it was not changing that much, because when the person, they was trying to stress the heart when they were doing exercise, trying to push them to do better exercise. And all the curves of the heart rate of everyone were like this, and then reaching the target heart rate, reaching very well. Whereas this guy was pretty much like this, and then staying here. And then the target heart rate was, the hell is going on here? And then I checked with the sport professional, and he told me, oh, that guy has a bypass. So you see, though, all those things are good to consider before, because you don't want to spend 3 hours recording data of this participant if that person is going to be able to exhibit the type of physiological response you were looking at. That's also a little bit tricky, because you don't want to ask the person in the screening question, oh, are you anxious? What is your level of anxiety? Is it like super high, super low? But, you don't want to get into that question, because then ethics will figure out. And beyond ethics is like, why do you care? I know this is research and it's important, but why do you care about my levels of anxiety? So, anyways, it's important to do any type of screening beforehand. So analysis. So we were just checking all the feature structure for IMU, EDA, and heart rate variability. What do you think, guys, are the most challenging aspects of analyzing these signals and kind of like trying to extract and choose?
Feature extraction, selecting appropriate window frequency.
So the windowing?
Yeah.
That's always a tricky aspect to consider. There's good literature pointed out like what are the window sizes for the specific signals, but you will see that also varies depending on the context. Like heart rate variability is one that really can change suddenly in just a couple of seconds, whereas the electrodermal activity or the respiration, that takes a long time to change or exhibit changes that are in response to the external stressors or stimuli that you're providing. Yeah.
I'd say like variance between the participants, so like you might be used to analyzing just a certain window of and then you might find people that just respond differently. So variance in your features.
Yeah, it's also tricky to find the tables that are telling you what are supposed to be the ranges of this specific data. So I mentioned the handbook of ECG, 1,000 pages handbook, but that took me, months to kind of like find that type of information. Whereas when you go to EDA, when you go to the others, it's like hard to find where are those ranges. So we'll say variability plus what's called the normative data.
Noise cancellation and the cleaning the data. Yeah.
Artifacts.
yeah. Signal versus noise.
Yes.
Mm-hmm. Yeah, there's always an index of signal versus noise and everything, but every signal is like they're coming with their own artifacts and things. So same thing you can apply for one signal is not always applicable to the other one.
Yeah, I think especially in the case that we were measuring like multiple signals, and usually like when you're doing like those kind of processing, you want to analyze the frequency domain, but a lot of the time like the noise from one signal is overlapping with the signal of another measure that you're doing. So you can't separate the signal between the noise and the measure. The contamination, like the crosstalk that you talked about. So.
Yeah. So we talk about this cross-talking. That happens a lot across especially electrodes that you do. But that also happens with all the signals. Like you put an optical sensor over here. So how do you know that the light is not intervening with it, or like some specific movement you do? So about the street, any other that you see from the top of your head?
Yeah, I don't have any experience in analysis, but analyzing, but I guess that picking up
Guess.
the right kind of algorithms for noise cancellation and for pre-processing can be tricky.
Indeed. We are just seeing these toolboxes to be released, and that's like, oh, cool, somebody did it. But in the past, it was like everyone, every lab, they were similar to what we have here. So it's like every lab is doing their own things. Like, how do you program Pepper depends on not like the architecture of Pepper, but basically what the lab wants to do with it. So everyone knows there's not a consensus or standardization on the algorithms to extract one thing or the other.
Also related with the signal versus noise is all the decisions that you have to make with the filter, the cutoff frequency that you're gonna use for each variable.
It's called I think it's modulation or tuning. It's called the tuning of the filters.
Yeah.
A lot of those filters, they have parameters to reduce and to increase and to let some things to happen and some others. So every time you tune some of these, there's changes in the signal that you sometimes don't really know if that's positively affecting your analysis or negatively affecting your analysis.
Yeah, sometimes you use the same filter, but then for a specific part, for example, yesterday when I was mentioning the heart rate, so we have to high pass it and then low pass it with a different cutoff frequency just to remove the heart rate noise when we are doing muscle activation analysis. So sometimes it's just use the same filter, but just to change that specific parameter of the cutoff frequency, and that's make like a whole change in the analysis.
Yeah.
Now I think the most important thing is lack of an expertise while doing all this thing. And imagine if I'm doing, I need to have a person who can assist me because this is not my expertise, right? And in this lab, if someone is doing that and if John is not here, who's gonna help?
I think that's and I think we mentioned this when we just started the workshop, is like this type of technology itself, it's always very sexy. Like, when you talk about physiological signals, oh cool, putting sensors and putting things there, but what I've seen unfortunately happening in many laboratories is sometimes they pay more attention to the amount of sensors they have and not necessarily the amount of expertise or infrastructure that they have to process those. So that happens a lot. I've seen many different sensors in many different laboratories and nobody's using them, or they use it and they go for the recording to the paper without keeping a consistent analysis of all of them. Yes.
But this is also, it is also because it is a multidisciplinary field and you need a doctor perhaps to understand the graphs. You need a person from to understand this kind of technology. You need a person, HRI.
Yeah, more
researchers.
input you have from people that have some knowledge with those signals, better you can, design your own system. That might explain, for instance, why there's not a lot of examples of physiological adaptive systems in a field as HRI, which is pretty much emerging. When I say emerging, it's like 10 to 20 years. Whereas you see physiological adaptive systems in medical devices, like the ventilators, they are actually closed-loop systems. So they record what is the level of oxygenation on your lungs, and then they supply the medicine based on those things that they're recording. So there's plenty of advancement there, but for these other signals or for these other applications, it's more complicated. Cool. So the last one will be translation. So we haven't talked that much about translation, but I just would like to sense which do you guys think would be like some of the challenges that we will find in.
Right? Latency would be a big one.
Latency.
From sensing to analysis to translation.
Can you elaborate more into the,
Like
or do you see that being a challenge?
Like by the time we get to the translation to make an action selection, like what we sensed might have been in the past. So I'm just saying, especially with the window size and then picking up that window size and analyzing that window size, realizing like, oh, we stressed this person out, we should probably do something to fix that, but the person's already calmed down the window or something.
When you say translation, what does it mean?
We were talking about the closing the loop.
So giving the feedback back to the user.
Yeah.
Okay.
This third stage, in which we know already, okay, this person is stressed. What do we do? How can we translate that into an actionable action into the system? That would be the translation side. So latency, yeah. Indeed, what I've seen in a couple of experiments is they switch from one condition to the other very quick. So and they try to record changes from one condition to the other without having enough window to record that. So when they switch from behavior A to a behavior B, that's probably 30 seconds, and you want to see, oh yeah, the EDA exposed this behavior during this, and that can be also related to what was happening in condition B. So you really need to do a good experimental design when bringing the stimulus.
I could think about here, I don't know if it should go in sensing, but time lag. So the moment that you're getting the translation and you want to give feedback to the user, is that the right moment or it's delayed?
Yeah. See, those are more like problems related to it's actually real time, with
sorry.
Wells? No, you.
Yeah, I would ask, so you then, because of the changes in different conditions, so you would suggest it's better to have one person in the same condition or the same person to experiment both of the conditions? I mean, in within or in between experiment?
Yeah, that's always one of the first questions that when it comes to experimental design I try to solve. And I will say there's not an answer that always applies to all the experiments. That sometimes is cool for you to show that the adaptation algorithm or the closed loop system that you were designing, it fits well when you bring different people.
Yeah.
So it adapts to the variability, the inter-subject variability. But sometimes you really want to test something that is more specific. You want to control the variability. You want to really control that variability. You rather expose people to the different conditions, the same person's different conditions. I did that with again some older adults, and I got them doing a type of exercise, and I exposed them to the system that was physiologically adaptive. They were exactly the same people, exactly the same time is also important thing. Exposition time, 20 minutes. 20 minutes, try to keep control of the amount of exposition that you have, and that not always happens when you're doing more like an open interaction with that. So timing the conditions is always, it facilitates a lot the
But
process.
it's a question of design of experiment and
Mhm.
the objective and goal of how you design and
Mhm.
what you want to measure.
Mhm.
But timing is important, I guess.
Yeah,
Conditions.
that's always tricky with those signals. Any other challenge you see?
I think one I could think. Anyways, it's not in my experience yet. What kind of feedback you want to give, and why do you want to give that feedback? Perhaps that feedback may increase stress, or I don't know. There's also ethics here.
Mm-hmm. Yeah, and that's part when you're trying to model your system, you're trying to persuade people towards having a specific behavior, but you are recording that by using physiological signals. So how can you ensure that the person is actually going to behave in that manner? So this is always part of the when you design your task, you really need to be sure that you are covering feedback that is going to be persuasive enough. The solution that I found for this is testing. Much the same. The second one is, okay, you just take your data, check the data, you make a machine learning algorithm to interpret that data and to give you the output. What is the limitation of this? You need data. So that means you need to run an experiment previously with the same kind of population using Wizard of Oz. So you just on and off the conditions, you check how people are on their resting or their low, medium, and very extreme situations, and then you make your own model based on this, and then you put that into the adaptation. So supervised, unsupervised, or reinforcement learning. There's some examples of this, but most of the applications that I've seen that actually work in real life are simple, keep it simple, on-off adaptation. So classic if-then adaptive rules. Before finishing, I wanted to, cover a little bit into the, closing the entire loop. The first part is sensing. So we have been mostly recording what we are sensing. So we have been wiring the sensors and we have been getting that into a file. But in order to create a real-time adaptation, you need to be able to access that data. So you need to be able to stream that data. And that's actually what Trevor has been doing with the shimmer devices. So we have the application for the polar chest strap. It gets you the data, it streams the data. I didn't show you, but you can actually capture that data in a port, and then you can play with the feature extraction algorithms. But you can also do the same thing with the shimmer device. It took some time for Trevor to build an application that it was actually able to get the data and stream the data. A lot of these sensors, they are not coming with a software that allows you to stream the data. The sensors are just there for recording the data, keeping data for your experiments. So what the last thing that I wanted to show you before the demo is actually what Trevor was doing with streaming data from the shimmer devices. So you can. So you're planning to work with the shimmers, and you're planning to create an adaptive system using one of the signals there. So you probably will have to use the tool that he just created. It's similar to you remember the application consensus Pro, so recording here then is you just select the sensor, select whatever you want to stream, but then he will show you that there is a specific protocol for you guys to be able to receive that data. It's in the controller? The controller? Oh, let me see here. Boom.
we have.
So we're still trying to solve problems here, which is sensing. So it is, okay, not only getting the signals, but also streaming the signals so you can capture those. Fortunately, the problems that we were mentioning here regarding standardization, there's some progress on it. So the people in biosensing and biomedical field are getting towards a standard on how to stream that data using the time series and using a specific tags and streams.
Yeah, so I guess I can introduce myself first. So I'm Trevor, I'm in 4th year of biomedical engineering, and so I was doing a undergraduate research assistantship here last fall. And so part of what I was working on, the system that John showed before, was basically being able to get the signals from one of these shimmer devices into a way that we can stream to the robots, and in particular this protocol called lab streaming layer, or LSL. And so previously, like LSL has been used a lot in EEG applications, particularly because EEG has like a lot of different signals. You know, you can be recording like 60 different areas of the brain and stuff, and so it's kind of a way to bring a lot of data and stream it at once into like common timestamps, for example, and then on another side, for example, for our applications robotics, be able to pick that up and then do something with it. And so essentially it's kind of just like, there's two sides of it. One of them is all the inputs, so every single input device you'd have has a way of packaging data in this protocol and then sending it into the LSL framework. And then on the other side, any kind of data consumer you want, either you're recording it or using it for robotics applications, can pull out those different streams of data, and you can select which streams you want, whichever sensors. For example, if you have multiple of these like shimmer devices streaming, you can just pick which sensor you want and then be able to plug that into your application. And so that's sort of the idea behind this, because it's one common framework that we can use.
Before these, like when you wanted to combine signals from multiple sensors, you kind of like needed to develop your own protocol. So what this protocol is trying to do is, independently we have shimmer devices, or we have the polar chassis trap, or we have in the future BCI systems, we will be able to stream the data that is coming from all those sensors using the same protocol. So if in the future we get more sensors, there's a person that will have to do what Trevor was doing, which is in a sense a software client. Software client calls the data that is being recorded from the signal, and it structures that data in a way that is organized and is well established already.
Yeah. So ideally, as a robotics researcher, all you would have to do is, take the outputs of the lab streaming layer, transform them into, the analysis you want, and then you build that analysis into your pipeline and provide that to the robot. And so again, because it's like, ideally, it's like device agnostic. It doesn't matter whether I have a shimmer device or a polar device. You could be able to plug multiple of these devices in and get multiple signals out.
Does it also synchronize the signals?
Yeah, so one of the nice features is it attempts to synchronize the timestamps, and so ideally when you're pulling from that stream, you should get a relatively clean timestamp, but it's possible that you don't, so that's part of your post-processing is if you're grabbing from multiple streams, being able to figure out how to synchronize those.
I would say that's the best feature of this protocol, because when it comes to what Christina was saying, you have a sensor. This is coming with one sampling frequency and the other is a different sampling frequency. The moment that you are trying to make a joint analysis of both, you will have time series that are different length. So, how do you know what was the reaction of the EDA and ECG if you're recording those from different sensors? So, what this protocol is helping you is to structure all of them using the same time step, so you know exactly when was the moment that will happen.
So pretty much what I worked on is making this in Python, and there's still definitely more work to make this usable, but this is sort of what I have right now. So essentially the shimmer devices can connect to Bluetooth, and that's how they connect to the consensus client, except all that consensus does is it sort of receives the data, and you can plot it, it can record it, but it can't really push that data into a lab streaming layer. So what I've been looking at is how to do that part. So I think I mentioned this back a couple days ago, but like consensus is great for the recording part, doing your analysis, figuring out, what kind of analysis you need to do, which signals are going to work best. But sort of once that's all figured out, this is sort of where this comes in, is being able to, figure out your sensors, pick whichever ones you want, and then be able to stream just the raw data somewhere so that you can process it later on. And so right now I have one of the devices that's connected by Bluetooth to this computer already, and be able to connect it here. And then
Before you go to the connection, I just want to be sure that it's clear, like why do we need to be doing this kind of tools? I mean, feel free like to say it is not clear for you.
Yeah, what I understood that for example, for shimmer devices, we already had this consensus, the application, but we didn't have any functionality to stream that data in real time. So what Trevor is doing is taking that data from consensus and streaming that data through this interface to the final robot or any user. That's what.
Yes. It's actually streaming it in a way that you can capture it using ROS or whatever other in Python.
Yeah.
There's a new device coming and you will like, why not using EEG for this one? Then what will you have to do? Develop another software client that connects that new piece of hardware with LSL. So that's why it's kind of like an initial steps for building infrastructure. But that facilitates the integration of multiple sensors. For instance, we have Toby. So if you want to include eye tracking in your experiment, so there's already a software client that is going to stream. So if you want to use eye tracking plus heart rate variability, so you just get two software that are different software clients. You click on streaming at the same time, and then they are both coming with the same timestamp using this protocol.
So right now, only shimmer devices are working, or other sensors as well with this?
So the application that I show you with the polar chest strap also streams using LSL. So right now you can combine polar and shimmer. There's, of course, because this is kind of like a standard for streaming time series, there's another people that have been also creating their own clients for other sensors. So there's already like PCI, EEG sensors that already talk to LSL. So if you want to include those, so you probably will be able to find those. There's a huge list of hardware tools that are already there available to stream data using this protocol.
So right now, like the basic thing it does is streaming, but definitely there's sort of a lot more area to improve this. But essentially, like there's a button to connect to Bluetooth, and now we've been able to find, okay, this device that I have here is connected, and sort of now I want to be able to set it up for streaming. So right now, there's sort of only these sensors that are set up. We haven't had any IMUs yet. But it could be potentially extended to include IMU, for example, if that's an application that you wanted to use it for. And so the important thing is being able to set what sensors you want, obviously, and then also the name of the stream is important. From the idea of like receiving the data, you need to know what stream you're looking for, so that when you get it, you can say, oh, okay, yes, I'm looking for this particular shimmer device and the stream here. So right now it's just called shimmer B022, which is just the name of the device. And here, we have GSR plugged in, so I'm going to select this one. Yep, and so that's attached here. And then essentially after that, we can click Start Streaming, and then it's going to be sending this into LSL. I don't have it right now, but ideally you would have some piece of software on the other side, and then it's going to be able to pick up and read out those values. John, I don't know if you have the picture, the presentation we did in the Zoom call. There's a picture there. Yeah, so I also was able to test this with multiple sensors too. So I'd have to find which ones are connected, but you could stream multiple of these devices as well. And so again, each of them would have a different name. And so let's say you wanted to pick up both of those, as long as you know the name, then you can say, okay, I would like shimmer B022 and B024, and be able to pick those out. I'm not pick any of the presentation.
First one?
Yeah. Yeah, this one. Yeah, so this is sort of like what it might look like. On another side, I have an example script, which is in the GitHub, which I think was been shared already.
Yeah,
you
should share,
Yeah.
you can share also the link to it.
Yeah, I can do that. But anyways, this is the output of that example script. And so basically we said like, oh, we're looking for a live stream layer stream, and we're able to find the shimmer through device, which is great. And then this particular name, I call it B0, B1, IMU. And then these are all the names of the channels that it streams. So then output kind of just looks something like this, which is like, oh, this is just a bunch of numbers. And so what it means is each of these stream names that we have, so acceleration, low noise acceleration X, that corresponds to the first value here. The low noise acceleration Y corresponds to this value here, and then et cetera down the line. So one of the things about the IMU at least is that because only streaming the raw values is not calibrated. And so that's probably one of the things, if you want to use IMU, you'll have to figure out beyond this. Right now it's just like, how are we going to do the calibration? Again, all we can do is just stream the values to you. You need to figure out how to correspond those into the real sensor values. For example, acceleration in meters per second squared, rather than just a number like 2,880. With the these ones though, the GSR, those ones do have conversions to units that are really easy. And so in this case, I've already programmed that in. It'll report the conductance or the resistance, and then the PPGs and millivolts. So it already records those units, so those are easier to use.
So you filter after you have the raw data and you find out the angles, you do the filter for the signal?
So this is not doing any pre-processing. All this is, like this currently right now, all it's doing is sending the raw bit values that the sensor reports. So for example, it'll report a number between minus 2048 and positive 20, or no more than that, I guess negative 4096 and positive 4096, and that's just the value of the sensor. So that first needs to be mapped into, like, yeah, the angle, angular acceleration, or the meters per second squared. And then from that, would still need to be further filtered according to whatever filters you've been using. And then if you want to do calibration on that as well, you would have to do that aspect for IMU.
But for example, so how do you know, for example, the polar beat, if the signal that is already streaming is already filtered or you're accessing the raw signal? Do you know that? Do you have a choice?
The polar gives you the labels. So it gives you like its heart rate, its heart interval, or is the raw ECG.
Okay.
So for the type of application we will do, you don't stream the raw ECG because, well, the sensor is already giving you the heart rate and heart intervals. Why do you want to stream that? So for these ones, you are actually streaming the raw data.
Yeah.
So if you want to use this one, you will need to include pre-processing, feature extraction, specifically for the RR intervals. For the polar, you kind of like simplify, at least for the heart rate, so you don't need to get to the pre-processing and extraction of RR intervals, but you only include the feature extraction algorithms for the time domain and frequency domain.
So like for the GSR, that's already in the correct units. More of that would be like just when doing filtering. If you wanted to only select, let's say, the samples at 40 hertz rather than like 2,000 hertz, you would do that sort of examples of pre-processing. Just for the IMU, it's just a lot more trickier because there's so much data coming in, and it's kind of hard to know which ones people want. I think one of the challenges with this as well is being able to do that real-time processing. And so, for example, if we're looking at Windows, right, you're not necessarily able to do the Fourier transform and get some of those lower frequencies. And so, oftentimes for real-time signal processing, you're going to be looking at those time domain statistical features. So those are just much easier to compute over a window basis. Like we mentioned latency as well. If you have a small enough window, you can compute those fast enough. It's not that, doesn't take as much time as doing a whole Fourier transform on like a 5-minute scale. So those are some things to keep in mind for doing more of the real-time closed loop systems.
Don't you find that when you're like filter at the end after you calculate the angles, it's not like an accumulation of a lot of errors? Whereas if you filter once you have the real data before doing all these things.
So that would be part of like the analysis part, is determining what filters, right? So if you're doing just sort of a simple low-pass filter, that can be computed like in real time with your signal.
Oh, you can do it in real time.
The best sensors that I've seen and I've used for these type of applications are the ones that are giving you already the features.
Yeah.
Well, I'm not saying best is because I'm interested in the front-end application. I'm not that much interested in how accurate is the computation of this feature, blah, blah, blah. No, I'm more, part of my research is the other. There's a lot of other people trying to see more the accuracy. So that's why, as I'm telling you, I mean, being able to play mostly with the polar and others, because they give me already the high frequencies or low frequencies. So every 5 seconds is throwing me that value. So I can kind of keep all that part, especially the algorithms that they are using. They are well done algorithms. Most of them are doing that. There's a company in Toronto that does wearable EEG, and they give you already the alpha, the beta, and the theta, and delta, which are the frequency domains of the EEG.
Yeah, so yeah, there are for sure, there's two kinds of accelerometers in here. So one of them is lower noise. It does filter a little bit, but it doesn't have the range of some of the other ones. So it's really a limited amount of the spectrum you might want. But again, for a lot of physiological applications, that's not a huge deal.
Things to consider when working with this protocol. It doesn't work with EduROM, so you need a specific and dedicated network to work with. The computers, they need to be synchronized, so they need to be in the same network. So that means my recommendation is define a computer for physiological sensing and streaming, and capture those signals using a different computer for the robot response. So sometimes when you're streaming among like 2 or 3 sensors, there's a lot of data going on there, so you don't want your computer to lag in performance. So you want a clean stream. So what the protocol actually does is allowing that streaming also in the same network, which is a cool feature.
Yeah, I guess that was mentioned. When you're doing the LSL, any device connected to that network is able to pick up the LSL with the right client. So we've done it in MATLAB before, I've done it in Python before. There's probably other applications that are just able to pick it up, and then you can programmatically extract whatever information as long as you're connected to that network.
This interface is just for Python, right?
This one I wrote is for Python, but I also did it on MATLAB,
Oh,
the
okay.
computer that had MATLAB on it. Yeah.
Perfect.
I just don't have it. I don't have it on my laptop, so I did it in Python. But yeah, both will work. And,
Okay.
It's a little older, MATLAB 2013.
No, that was for my guide user interface. I downloaded the 2013 and it's not working either, so I don't know what they do with those things.
Yeah.
But no, I think the one that you're mentioning, it doesn't, it works well with the 2021
Yeah.
version.
And so again, the idea is you just have this one computer set up, connected to whatever sensors you're streaming, and just leave this running. And then, on your other computer, picking up those signals, sending those to the robots, and doing that kind of processing.
Is that first value that they give you, is that the time on it, the timestamp?
Yeah, so this is the timestamp that the LSL gives you.
It's an internal clock, is that the internal?
No, I think you might have to do a bit more processing of what that timestamp means. But that's the timestamp that LSL gives. That might be for example, an integer like Linux epochs in seconds or something like that. So that might still have to be further converted, but I just
Most of the time what you do in your pipeline is you just start streaming.
yeah.
And then when you pipeline, you just, when you interface a robot, then you have a start experiment button. And what that's going to do is just going to pull the data, and then you put the time 0 right when you're starting the experiment. So you don't necessarily care that much about what is the timestamp of the stream data, but the one that you put has 0.
But whatever it is across all of the LSL streams, this timestamp will be consistent.
Mhm.
So even though the other stream might be offset a little bit, 4073 is going to be close to the 4073 of the other stream. Whereas the shimmer sensors themselves could be outputting different timestamps.
Sorry, I have something. No, sorry. Go ahead.
I was just gonna ask, the variants, the first 3 are 51, 51, 51. After this one, we jumped to almost 54. Is that just a delay in the device for the streaming?
Which data?
Right here.
They're jumping by different amounts.
It was going real time, and then there's a bit of a delay between the
Yeah, so it's whenever it's able to pull the sample down. So that could be because the shimmer device wasn't able to send it. It could be because this laptop that's streaming it wasn't able to send it. It could be the laptop that's receiving it wasn't able to
Wasn't
pull it
the
in time.
network.
So network congestion.
Yeah, so it's not necessarily always going to be on perfect intervals, it's whatever, it's whenever the next sample is ready that you can get it.
Yeah.
That's not the fun.
Well, you certainly might lose some packages,
Right.
but believe me, this protocol is the most efficient thing to avoid you losing packages. So what was before this,
Yeah.
at some point, you just didn't know what was happening, or when you plot the data, you see like, oh, cool, then, and then coming back again. So that data is like, oh, you need to discard that data because you lose a lot of packages in the streaming.
I feel like if you want to make sure you don't lose any packages, now you're dealing with time. Like any protocol that super secure on packages, you're gonna takes a lot more time. So.
Yeah. So this is the one that is probably most efficient
Yeah.
for avoiding losing packages.
What if you create an event? In one sense is, what if you create an event? Does it show it or in the interface as well?
So that was another thing that I was able to do is like creating events here, but I think it would not be like a very difficult extension to do is just to have a button to create events and also push back into live streaming layer. Because like essentially what live streaming layer does is just asking, oh, should I put something in? Yes or no? And like, you know, these sensors, every time they generate a new data point, they just push it into live streaming layer. And you can very much do the same thing with just the computer doing it.
Okay.
You can do something, you can fake it, right? So you can create a fake device of events, which is a keyboard, for example, that streams to LSL. So it will be synchronized in the same network. You just click one button and it sends one signal, and that is your event.
Yeah, that's also part of your pipeline. Like when you're working with the robot and you want to know exactly when you were activating the behavior of the robot, then you just put the data into the same stream and you send it to LSL so you know what time it is. You assign it to a keyboard. I think that's what I would do to make it simple.
Yeah.
So, I don't see you guys being very excited about creating physiological adaptive systems. That was not the purpose of this workshop is somehow to show you that, in order to create these type of applications, there's some things that you need to consider before jumping to, what signal and, what is the adaptation and all those things. We have created some infrastructure there, so there's already some software tools that you can create. I'm going to put everything on a single website of the workshop plus with the videos and a picture. We're going to take a picture. And we will have everything there up and running for you to be able to access. So we have a repository with all the scripts, with the what we were able to do with the HRI Physio lead. And we even have some scripts that are capable of receiving data directly in ROS using LSL. So you have a robot already running in ROS, so you can use that script to collect those. There is even one example that Austin was doing related to the adaptation with QT robot, so you can see some of the behavior and how we were, he was triggering some of that behavior. Questions?
So you'll assist us when we need to use Physiological?
Yeah, I can always help you, with the variables and all the things, and how to use some of these software tools and things like that. To be honest, most of the times what I've seen a lot of students failing is in not planning. Like that means getting very excited about hiring, using a lot of sensors and a lot of signals, and not defining pretty well what are the features, what are the methods that you will use, and simplifying. I think here in engineering we have this bad habit of making things super complicated without the need of those being super complicated. Just because it's the most recent machine learning, adaptive technology, and deep learning, and we want to use that because otherwise we are not going to impact on science. When it comes to physiological adaptive systems, that doesn't apply. It applies simple things that might work. It doesn't apply.
It's a real-time application. When you apply in real-time situations, you need to be practical.
And simple.
Yeah.
So that's why in the review that I did, most of the physiological adaptive systems were using control theoretics, on, off, or even PID controllers, but you know, there was not a lot using machine learning ones. So keep it simple. There's already a lot of complexities there with the processing. To not keep the adaptation rule simple.
I still think machine learning can be very complicated because, like you said, but you need to collect the data beforehand. You need to have data for any machine learning algorithm, and you need to collect that data before. If you are doing that experiment first time,
Thank you, Trevor.
then when you would collect the data and when you will apply.
Yeah, that's yeah, that's more or less what I gain experiences with all of this data. So yeah, try to keep it simple.
Question. So, physiological signals are so basically they're delayed, right? So they're not, I mean, you read them a bit delayed because we are slow with everything. From your experience, is there a way that you could find tendencies or kind of predict? So maybe you see the heartbeat slightly going up and up, so maybe then you can see, okay, this has a tendency to go up, so maybe before it reaches a big peak, you can react beforehand. So can you kind of predict based on some of the data that you're accumulating?
Well, that's certainly what you want in your system. Like if you want to assist, you don't want to wait for the person to get a super high levels and then, oh yeah, now why did we change it? No, you want to kind of do it before. Yes, so you need to basically try to find studies under similar contexts, under similar populations, where they were recording that signal that you were seeing, so you can have more or less a good knowledge of what you expect of having. They're hard to, it's hard to get to like good information about that, but what I've been trying to do is something that, just briefly here. I mean, in an ideal world, what you will have is something that is called psychophysiological model, which is basically under this specific situation, dealing with the psychological states, this is how the physiological signals react. So if you have that beforehand, boom, that's half a way of creating an adaptive system. So and thus, what I have been trying to do in some experiments I do with VR is actually creating the model beforehand, so then you can create the adaptive rule. The way that they look, so the way that a psychophysiological model will look like is, I mean, it's more or less, I mean, a simplified way. You don't want something extremely complex. But, you know, after that you do all the analysis of the signals and then you know how people react to it, what you will have is something like this in a simplified manner. So before going to the adaptive system, so I exposed people, in this case they were police officers that were going on their virtual reality training using firearms. So I hooked them with a polar strap and I hooked them with the EEG wearable device. So I did kind of like Wizard of Oz. I was modifying the difficulty of the simulator. So at the beginning they were shooting, the targets were static. So it was pretty easy for them to shoot. Then that was 3 minutes. Then I moved to a medium, so the targets started moving to speed. So it was a little bit more, you know, hectic things happening. So that was my medium, and then I pushed to frustrate them. So the targets were moving crazy. So they were, of course, they were police officers. The trainer was just outside sitting there, so the level of stress that they were exerting was a little bit high. So I pushed to frustrate them. And again, I did 3 minutes. So I got this chunk of data, heart rate variability and EEG data, and I started seeing, okay, from this, and I collected baseline. So from all of these conditions, what are the metrics that I have that are better to discriminate among them? Baseline, easy, medium, or hard. So I then ended up with, okay, there's a calmness metric with the heart rate. Heart rate was the best to discriminate across this tree in terms of significant differences. And EEG was the frontal theta, which is one of the frequency bands that you have from EEG. So I got that one, and then I just plot them over here. And here you can see the heart rate was behaving like that, similar to what we saw in the arousal thing. So when they were very much engaged, easy and medium, it was still doable for them. The heart rate was going up, but not a lot. These are average of the 10 police officers that I was doing that. You see, the numbers are not like super crazy. And it took me fairly a decent amount of time to create this model. So for the frontal theta, the same thing was increasing, and then things were decreasing.
What is the frontal theta? What does it?
Is a frequency component of the EEG data in the frontal lobe, similar to high frequency and low frequency in a specific range.
When it goes down, when is it getting harder? So does it mean that it...
Yeah, that means that that's the behavior they're exhibiting when they're getting frustrated. So this is kind of like frustration.
Okay.
So that was the metric that better differentiate between baseline, easy, medium, hard. So once I have this, then I can move to create my adaptive rules. So once you have, I mean, this is the kind of like the ideal case where you have a model for that. But most of the times you don't have a model. So, and then you move to, okay, once I know this, then I have a software that was created in Unity. Then I say, okay, now I can create a simple adaptive rule. So you collect the heart rate, you collect the theta, frontal theta in real time, and then you merge those two. You say, okay, I make an array, 10 seconds, I check the 10 seconds data for heart rate and frontal theta, and then I check the constants. So I know the values in which, okay, if this changes is because the person is getting frustrated or stressed. Heart rate was up of 100 BPMs, so people were getting a little bit more into the medium. So once these things are changing, that's why I'm comparing one, this is bigger than or less than, then I was changing something into the simulation. So the simulation was getting harder when they were getting a little bit more stress. So that was, it's kind of like a simple way to create that adaptive rule. But that's why, ideally, having a psychophysiological model is good. So you know which features are better to discriminate across conditions, and you know the values, and then you can create the adaptive rule. And this is, simplistic if-then rule. So I didn't put a lot of sophistication into it, and it was already very complex to do. I needed NASA scientists to actually be able to help me. So that's how complex it is.
So what's the practicality going forward? You can't expect in the future everyone to have like sensors on them when you're interacting with robots. Is it one day to hopefully operate on just a smart watch or something?
Yeah, I think it's going to reduce in terms of how obtrusive they are. It's going to, the access to the information is going to be easier. So right now you cannot access to a lot of the raw data of the wearables that you have. They don't like that. It's like, oh no, just go through my interface, Apple, and then, through my interface, then you can't get it there. But if you try to get the heart rate data from the Apple, it's like, or not even the heart rate, you probably could get the heart rate, but then you say, no, don't give me the heart rate, give me the wave form of the BPE, they say. They don't like that. So what I'm expecting is more and more manufacturers allowing people to get the data in a more transparent manner. And then we're moving more towards the ethics application of all, or implications of all of those things. But that's what I'm expecting. And I will, also expect to be able to create some applications using the robots that we have here in the lab, because this is a field that hasn't been explored yet in a human-robot interaction scenario.